Yeah. I think I turned on. Yeah. Hope this helps.
Yes.
Yeah. Okay, sounds good. Sorry, for audience in the Zoom, I'll probably go over this slide one more time. Sorry for the actual audience for listening this twice. So the main question I want to address in this problem is the following. As mentioned directly, I would like to answer that question. Is there a robust estimator that works in general parameter space? And here, I want to emphasize two aspects. First one is robustness. Like there are kind of robustness is kind of some abstract. There's one more chatting. Let me just check that. Okay, so it goes. Robustness is something we kind of know all vaguely at least or intuitively. Like it's often said that median is more robust than mean. But like I want to emphasize in what aspect, like what criterion you say median is more robust than mean. And second aspect I want to emphasize is parameter space. So if your data is in a vector, a mean of vectors, which is a parameter of the distribution, rely on the Euclidean space. And there's also covariance metrics. We are often asking about parameters and covariance estimators. Covariance metrics is in a line in a space of symmetric positive definite matrices, which I'll just shortly say SPD for all of these talks. So they're kind of, so my question is those like interaction between these two may get complicated. For example, robust methods which are often developed in Euclidean space or even more simply in just real line does not directly kind of extend to the general metric spaces. Let me take an example here. So median, we all know what median is. It's half rank quantity. But what does it mean to take a median of vectors or covariance matrices? So like here's the first kind of thing where this interaction between these two aspects gets more complicated. And our claim, I'll probably state the answer first here. Certain robustification methods, which will be later introduced as a Freshian median, can be extended to some very general metric spaces. So my claim is that to the main question, the answer is yes, and so such a robust estimator will be kind of Freshian median. Is there any question about these slides? All right, good. So I think the main takeaway is that interaction between this robustness and general parameter space may get complicated, but in certain situations, we get very nice estimators, Freshian median, to general metric spaces, which is denoted as kappa spaces. I'll definitely introduce what this means in the later slides, but let's take it granted that it's kind of certain methods works well for general metric spaces. Right. So let me go over those two aspects more detail. Robust estimations. There are many notions of robustness. It's kind of core interest in statistics. One may think of breakdown points. One may think of influence functions. But in this talk, I want to focus on this property. So in this work, robustness will stand for tail concentration. The estimator will be more robust if you have a faster concentration. I think it's kind of good to see the example. So let's say xi's are just normal. Let's basically think the real line just number. And if xi's are following IID normal with some mean, then our sample mean, x bar, will concentrate in an exponential e to the minus c and t squared. You can show this by either exact calculation. We have the normal distribution, or you can use the Bernstein equality since it's a sub-Gaussian. But the point is that like you can see the like minus n term in the power of exponential. So it's saying like it's kind of concentrating to the true mean very rapidly in a very rapid speed. But let's think another random variable, which I denoted as yi. This can be any distribution with a finite second moment. And in this case, all we can say is using the basic Chebyshev inequality, which will show that this tail probability will be like 1 over n t squared term. So here, there you can see the difference. Like as in n increases, this first example will concentrate very fastly, meaning that this probability go to zero very quickly. While in the second case, this probability goes to zero definitely, but in a slower rate than first one. So in this case, we sometimes say the first one is more robust than second one because it can work better with the small samples. So why this robustness matters? Because like we don't know the true distribution in practice, so sometimes true distribution might have a very heavy tail. And in that case, we cannot use this kind of Bernstein inequality or those exact distribution settings to measure the concentration. So we can only rely on Chebyshev inequality, and this will make the kind of slower convergence rate or concentration rate more. And in fact, this is true. So many standard estimators we are considering is in fact kind of cannot be fail to be robust, I would say, in a heavy tail setting. Is kind of like if you don't have those kind of normality assumptions, you cannot say it concentrates very fast. Any questions about this? Good. So I think it's so. So as I mentioned, I'm emphasizing two aspects. First is robustness, and as the main takeaway from here is that many estimators, in fact, fail to be robust. So we need some modification to the estimator to be robust under very general setting. And the second aspect I mentioned was if like space beyond the Euclidean spaces, we often encounter parameters that are not in a Euclidean space. For example, like even for like if your data has kind of infinite dimensional spaces like Hilbert space or Banach space, which are frequent in non-parametric estimation or functional data analysis. In that case, your data lies in this Hilbert space or Banach space, and if you just simply consider the mean of those kind of elements, they are no longer in a Euclidean space. Or you can think of Riemannian manifolds, which, like in directional statistics, hyperspheres are often, like data are represented in hyperspheres and for spatial statistics. And most commonly, you have covariance matrix estimation problem where your parameter now lies in this SPD space. Also, there might be a discrete space trees and graphs, which are often used in hierarchical models or graphical model, network data analysis. And in all of those cases, you can think of the parameters, data or parameter lying in some different space other than Euclidean space. So you might need some different methods for those data or parameters. So whether existing methods works generally well for these kind of more abstract or kind of non-standard spaces is kind of an important question, I would say. So, any questions? Yes.
Yes, I have a question from the previous slide.
Yeah.
So your claim will be like showing that estimators will have this type of exponential field?
Yes, my claim would be showing that like yes, my claim would be showing that we can construct an estimator that concentrates exponentially without any kind of tail assumptions. Your tail assumption means for this kind of normality assumption or more generally sub-Gaussian or sub-exponential type assumption on the data. Good. So I think I've done with the introduction, and as I mentioned, main takeaway is there is a certain robustification methods that works in general metric spaces. And so I'll move on with the preliminaries where I'll kind of now introduce those buzzwords in more detail. So first one is kappa space, which seems very kind of strange. This is a very general metric space equipped with kind of geometric structure, but hopefully I would say it's kind of minimal for our purpose. So informal statement would be follows. So kappa space is kind of a metric space that whose curvature is upper bounded by kappa. So it's still kind of very vague because I haven't introduced what really curvature means here. So in curvature, like there are a lot of notions of curvature, particularly in Riemannian manifolds. There are a lot of curvature, sectional curvature, scalar curvature, ridge curvature type thing. But here it's kind of more intuitive and geometric. So here we say how curved a space will be determined by comparing a triangle in our space X with a triangle in two-dimensional kappa curved space. What I mean by kappa curved space, it would be better to take an example for kappa larger than zero, or kappa equals zero. So kappa equals zero, it's a two-dimensional space with zero curvature space. So this is a Euclidean, like R2 in when kappa is zero. And if kappa is larger, you will take the two-dimensional sphere and you will draw a triangle over there. So you are comparing whether this our space's triangle is either fatter or thinner than the space in a circle or sphere. Let me use the boards. It's fine. So if I have this kind of two-dimensional sphere, our triangle should look like something like this. So this is kind of, we are, as curvature grows, we are kind of getting the fatter triangle than plain Euclidean triangle. So we're basically comparing whether our space's triangle is fatter than these type of triangles. And if kappa is smaller than zero, you will get kind of thinner triangle. So there's kind of, while incorrect, there's kind of vague expression for this, what I mean by that. So when kappa is larger than zero, this purple triangle, which has some kind of fat shape, will be the triangle in the model space. If kappa equals zero, that's the triangle we know in Euclidean space. And when kappa is smaller than zero, you will have this kind of thinner triangle. And in fact, those like whether triangles are fatter or thinner, you can see by these angles. If triangles get fatter, angles get larger in fact. And if triangles are thinner, angles get smaller. So our cat kappa space means like we are considering some small triangle in X. And if it's thinner than triangle in kappa space, we say it's a cat kappa space. So it's in this sense, it's kind of bounded curvature by kappa in the sense that we do not have any fatter triangle than kappa triangle. So this notion of curvature is called Alexandrov curvature, and this is in fact generalization of Riemannian sectional curvature for in case who are interested in this geometric structure. And any question of this? So yeah, I would say while it looks technical about these kind of hyperbolic spaces or those kind of things, I would say just remember like we just want to consider triangles that are not fatter than kappa triangle. So let me show some examples of kappa spaces, why we want to consider those kind of things. First of all, as I mentioned, this Alexandrov curvature is kind of generalization of sectional curvature in Riemannian manifolds. So Riemannian manifolds whose sectional curvatures are bounded upper bounded by kappa will be all kind of kappa spaces. For example, Euclidean space, your curvature is bounded by zero. Hypersphere, your curvatures are bounded by one. And like hyperbolic space, its curvature is even negative, and many like in many statistical like manifolds in information geometry, a lot of those you can upper bound the sectional curvature so that they can be a kappa space, and SPD matrix space with some appropriate metrics. Also, you can make it to be kappa or even Riemannian manifolds. And not only Riemannian manifolds, this includes infinite dimensional Hilbert space and like space of phylogenetic trees. These are some data type used in biology. I think the like Susan Holmes in Stanford are kind of expert in this phylogenetic trees. And there's metric graphs and trees. Like this is kind of nice thing because like in kind of Riemannian or Euclidean thing, it's hard to include this geometry of discrete spaces. But this kappa space is we can include the geometry of those discrete spaces as well. So any metric graphs with the cycles of length less than 2 pi is kappa 1, ket 1, sorry. Metric trees are ket 0, so it's non-positive. So, and ket 0 spaces, meaning that it's not fatter than Euclidean triangle, so it's often called non-positively curved spaces, and it's so-called NPC spaces, and this takes some particular role in mathematics, more kind of pure mathematics, so they have some separate names. And I didn't mention, but like there's also non-negative curved spaces where you cannot have the thinner triangle in Euclidean space, but that's kind of later story. So, any questions about these ket kappa spaces? Okay, good. Let me move on to the next section, which so I've introduced kind of what is it I mean by kind of general metric spaces, and let me go over what now I mean by median in those metric spaces. So actually mean and median are generalization of Euclidean mean and median. And let's take an analogy about it from Euclidean. So Euclidean mean, one way to define the Euclidean mean is your expected squared loss minimizer, right? And median, you can define kind of same thing. It's expected like minimizer, distance minimizer. So this definition, if you see that, you can check that this definition only is kind of can be generalized very vaguely to the metric spaces if we just substitute this norm by the distances. So that's what just written here. So if it's a kind of minimizing the expected squared distance between the measure and the point, then it's called a Fresher mean. And if it's just minimizing the p equals 1, it's just expected distance, then it's called a Fresher median. So I think you can just take this analogy directly to here. So any questions? Good. Some literatures use the term barycenter instead of pressure mean, and like geometric median instead of pressure median. So just in case anyone's interested, and of course, like we defined some new notion of like kind of mean and median. So we want to check whether this makes sense. So mathematicians already studied the existence and uniqueness of pressure mean and median. And in NPC space, as I mentioned, NPC space is non-positively curved space. Those pressure mean and medians are kind of very, very well defined. But now, if you're no longer in NPC space, there's some kind of additional technicality required to kind of guarantee the existence and uniqueness, which I'll not probably mention those fully detailed. Maybe you can refer our paper or some other literatures, but the main point is that at least these are not kind of some vague concepts. At least these can be defined under some certain circumstances. And just want to note that this is one way to define the Euclidean mean, but this is not the only way to define the Euclidean mean. And based on this kind of different, like things happen in mathematics, like, so we have bunch of equivalent definitions, but if you generalize each definitions, you get a different thing in more general spaces. That kind of happens here. So there are a lot of other notions of mean and median. So like there's some called inductive mean or convex mean or tournament-based median or Tukey step-based median, and all those coincide in very nice setting, for example, in real line. But if you go beyond the real line, those concepts may not match each other. So yes.
Going back to box, yes, here the mean you are using in metric, right?
Right.
So when you change this thing, like you still define the pressure mean, but it's for a different metric.
Yeah.
The examples you gave in the next slide are based on those changing the using different metrics.
Oh no, it's totally different. So like if you define the metric, then you can define any pressure mean, but these are totally different. Like even in the same metric, you can define the different means there. For example, this inductive mean is constructed by like inductively interpolating the geodesics in the space. When convex mean is defined kind of minimizer of any kind of convex operating like convex operation. Like even in the same metric, you can define those means and medians differently. So good. Thanks for the question. And so since we know that, I think we're making, yeah, I think we're clear with this slide. So let's go on to the next one. So last preliminary will be median of means, which is the classical estimator in this robust statistics like context. It's an estimator achieving exponential concentration under the only moment condition without any kind of tail assumptions. So basic constructions follows. So split the n data into k blocks and obtain the sample mean from each k blocks instead of obtaining the sample mean from n or entire n. Then you have a k number of sample means. You take a median of these k sample means. So you're kind of averaging between the mean and median, and you want to estimate the mean, but you want to take advantage of robustness of median from here. And this is proven to be concentrated to mean exponentially under Y setting, for example. In real life, it's kind of known for old time, like from very old, like long ago. And if it's in a Banach space, Minsker in 2025 proved that this median of means concentrate exponentially, and some Riemannian manifolds, it's lean by 2020. Yeah, so main point is that like not even for the mean, if you have the if you have the k different estimators, by taking the median of those estimators, you can kind of make it exponentially concentrate. That's kind of already proved in previous contexts for some spaces, Banach space or some Riemannian manifolds. And our finding is that kind of how, like up to which space we can generalize this phenomena. And our finding is like up to the kappa space, this is fine. And I conjecture that no more than ket kappa, this is possible. That's the conjecture. Anyways, so our finding is this taking FMOE, which I'll mention, Frechet median of estimators. So you're taking a Frechet median of the estimators. This can be generalized up to ket kappa space. Generalized mean in the sense that it still preserves the robustness. And yeah, so as I mentioned, there are different notions of medians in this, like different notions of medians even in the same metric space. And if you take a different notion of medians, you can get a different notion of median of means estimator. Those may not be coincide, but yeah. So any questions from up to here? Yes, sounds good. So I think main takeaway from this is this fresh median of estimators. So if you have some estimators that weakly concentrating, by taking a median, you get a strongly concentrating estimator. So you're kind of boosting your weak estimators to get the stronger concentration. So this is in fact kind of just all of my talk. So I'll go into the main theorem, which I'll not go too deeply because it's kind of very technically written. But so as I mentioned, our results will basically say that taking a fresh median of weakly concentrating estimators will get a strongly concentrating estimator. So and the reason this works is because fresh median has very nice property in a geometric sense. So let's say we give the ket kappa space and fix the data x1 to xk. So there's no randomness here, I want to mention. And you take an empirical pressure median of this x1 to xk called x star, and ignore these bunch of like ugly constants, and let's focus on just k kappa smaller or equal to 0. So let's focus on MPC space. And suppose there exists z, that distance from median and z is sufficiently far. That's just all the takeaway from this. So we have a z that's far from x star. And then there exists a subset of cardinality large enough. So there are bulk of points such that xj's are also far from z. So ignore all the kind of these words, and in a simple words, it's kind of, you're saying that if point Z is far away from fresh and median X star, then Z also has to be far away from bulk of the points in. So this is kind of just purely geometric property of the median. Like there's no randomness here. It's just empirical median aggregates the point very strongly. So this property of median is sometimes referred to majority voting in some literature. So you're kind of voting medians vote to majority, so that it's kind of preserving the property the majority of points will have. So is this clear? I think this lemma is kind of the most key of our analysis. So it's just good to take away this, like take this sentence, like so. And if kappa is larger than 0, you need kind of bunch of additional conditions, and this is in fact the unfavorable property of this fresh and median in ket kappa larger than 0. So like there's some additional conditions required, and this is reflected to this kind of bunch of ugly conditions. But still, main takeaway is as far as your curvature is bounded, this fresh and median will have this nice geometric property. And the proof idea is in fact quite simple. So ket kappa structure allows us to construct a triangle, and we can compare the triangle with a kappa triangle. And kappa triangle is kind of very explicit space. It's either two-dimensional hypersphere or two-dimensional like hyperbolic space. There are explicit calculation rules for some geometric quantities. For example, you can compute the angles in this space directly. So what we will do is we will assume that this claim is false, meaning that so this property does not hold. Then this X star is a median, meaning that it's kind of actually minimizer of the sum of the distances. And we show that this will never happen. So there's a contradiction. And so I think it's better to refer the paper, but main takeaway from this proof idea is that we need the curvature bound to do everything. And that's why our minimal kind of geometric structure becomes a kappa space. So sound good. I think the main takeaway is just meaning of the lemma, and that the role of curvature is essential to get this meaning of the lemma. And once you get the lemma, you will directly get our main result, which denotes that, like, let's say we have an estimator, K estimators, weakly concentrating. So this is written, here. So if we have K estimators that concentrates weakly to the true parameter, then if we take fresh and median of these estimators, this will have some exponential term appear here, which will make the exponential concentration in later publications. So this is basically just rewriting what all I've talked about. So if we have some weakly concentrating estimator, by taking a fresh and median of those estimators, we can make it convert concentration more strongly, meaning that we make a robust estimate. So basically, the idea is very, very simple. The event, this this is the event we want, is subset of this event because of the lemma. Because of lemma, So because of lemma, we have a bulk point sufficiently far away from X. So here now Z is the true parameter, X star is a median, and Xj is a parameter. So if true is far away from median, then true must be far away from bulk of the points. So this relationship is written here. And then this thing is some of the indicators. So this thing you can easily translate into binomial random variable and then use the turnoff bound to get the exponential. Any questions? Yes.
Can you go back to your question? Here the result you are getting is the same where the number of independent estimates.
Right. Number of subsets we can take.
Yeah, probably you are dividing n
No, it's K. K is correct, but in the later section, we will show that in fact this will make the exponential concentration for some. If P is polynomially decaying, this will make the exponential on N. Yeah, this will be X. This will be mentioned later. So, yes.
What is a sufficiently large K?
That's also something we will mention later when we go to the application section, but K in fact doesn't have to be too large, and the reason is follows. So K is a number of subsets. So in each subset, think of each subset, you will have N over K data, right? And as long as this, like what we will show later, is as long as this each subset estimator concentrates at least in some sense, then we will get the concentration, exponential concentration. And as I mentioned, this will be kind of, P will be like polynomial with respect to the number of data. And in this case, number of data will be N over K. So this P will be K over N. So as long as K over N is not too large, we will get our goal. So K over N not large means that K can be arbitrarily small, in fact, not arbitrarily, but K can be in fact O1, then it will concentrate polynomially. But I think it's better to write. In K subset, you will have N over K number of data. So if our estimators concentrate polynomially, it means it's N over K to some alpha. So if K is O1, this will have just this. So as long like it will be shown later that as long as our estimators concentrates just subset estimators concentrates in some sense, then we will get the exponential concentration. So K doesn't have to be too large. All right, so just main takeaway from here is that whenever an estimator concentrates weakly, applying the Freshen median of those estimators will make the estimator concentrate strongly. So this is essentially all the things. And just want to note that our extension covers almost all the previous analysis on this Freshen median of estimators, except the Banach space case. Banach space are not kappa space, and this is the only gap we have. Okay. And yeah, I think I'll have to go quickly, so I'll probably skip this algorithmic perspective. It's just basically saying that you can compute the Freshen median in many cases, and time complexity will not be too bad. So let me jump to the statistical applications. And first thing I want to mention is robust as Freshen mean estimations in MPC spaces. So basically, as the theorem says, what we only need is just weakly concentrating estimators, and we can take a Freshen median to make it strongly concentrate. So the matter boils down to whether we can get any estimator that concentrates at least weakly. So in NPC spaces, if you want to estimate the mean, we can think of empirical Freshen mean, meaning that instead of as going back and forth. So here you now take a sample mean and take a minimizer of sample means. That will be the empirical Freshen mean. And this empirical Freshen mean concentrates weakly. This is just what I'm saying in this theory proposition. And this, while it looks very trivial because in Euclidean mean, this will be in fact equal. But this is not that much trivial because you don't have those summation operation generally defined in metric spaces. But you can use the curvature comparison, in fact, to show that it becomes an inequality. So this gets always smaller, and then you apply the Chebyshev inequality or Markov inequality to obtain this thing. So one note is that while this looks trivial, this is not always guaranteed when you go beyond the MPC spaces. If you have positive curvature, like you cannot guarantee even this polynomial concentration of the means. So once we have this weakly concentrating estimators, we can directly take a pressure median and show that it concentrates exponentially. Like if you rewrite this term into t, this will become e to the minus n to the t plus t square, in fact. So, but like, I want to mention that in MPC spaces, to get the exponential concentration of just empirical pressure mean, in fact, we need some strong sub-Gaussian conditions. So our estimators is better in this sense because we still achieve the exponential concentration without those sub-Gaussian conditions. So as I mentioned, the proof idea goes as follows. So as I mentioned on the question for Isaac, thanks Isaac. And so here you will have the estimator weakly concentrating, and you define it by P in our theorem. And you apply our theorem, you will have the e to the minus k psi p type thing. And you optimize the bound with respect to p and alpha. So you choose optimal p and alpha, and you can get these type of bounds. Right. So this is pressure mean estimation problem. And note that this k here, k does not depend on n, as I mentioned. So this kind of justifies the claim over there. So k does not have to grow with respect to n. Right, and that's obviously.
What is the psi?
Oh, sorry, I didn't mention properly, but psi is just some function of that defined on alpha and d. And our theorem says it's exponential minus kappa psi, which appears because of those binomial construction. But this is just technical detail. And main point is that you can optimize this bound with respect to the alpha and d, and that will induce the desired results. Yeah. Yeah, delta should be dependent because of.
Then you choose a given tail. When you choose a given cutoff.
Yeah, that's gotta make sense because otherwise to control the tail we need some control on the we need some kind of things to get control of the delta. Yeah, and that's the K. Yeah. Yes, and that's in fact might be problematic. I'll mention in a conclusion, but yes, yeah. So I'll probably skip the covariance estimation problem. This is just basically saying the same thing. So you can define some metrics in a SPD matrices spaces, and like you can take any original estimator. For example, you can take a sample covariance matrix, and as long as you can show that this concentrates polynomially with respect to our desired metric, taking a pressure median will make the exponential concentration. So this is basically saying the same thing. And the main takeaway from here is that, like, unlike the previous example, we don't have to use the kind of those original estimator to be sample mean type thing. So here, like we define the original estimators that's not relevant to the metrics we define in this case. But as long as they concentrate polynomially, we can still apply them. So these are some numerical experiments. I did some covariance estimation problem, which I think this histogram shows the nice result. This red is the 95% confidence interval constructed from ours. And this green is confidence interval of just sample covariance metrics. So and our setting is we follow xi's are following t distributions, which is a heavy tail distribution. And we show that our estimator concentrates much more rapidly. So to jump to the conclusion, taking pressure median of estimators will make the estimator more robust. And this phenomenon can be extended up to general metric spaces for kappa space, which the core ingredient was curvature upper bounds and how they relate to the geometric property of the median. And yeah, and I would like to mention some limitations and further ones I'm considering. So as I mentioned, oh sorry. Our estimator is nearly fully implement. Sorry, our estimator nearly covers all the kind of previous literature, but not the Banach space case because Banach space is not a Kappa space, and the reason is the Banach space doesn't have an inner product structure. So this is likely a gap, and I think this can be overcome, but unfortunately, I don't think like I think this can be overcome, but I'm not going to pursue that direction. And a more interesting question I'm considering is following, whether we can overcome the curvature upper bound condition. And conjecturally, our analysis says that curvature upper bound is essential if you want to use the fresh median. So to avoid the use of like curvature upper bound, you need some other notion of median or other notion of robustness. That's mainly the one thing I'm thinking of because there are a lot of interesting spaces that doesn't have a curvature upper bound. Wasserstein space is one example. And maybe in this case, like trimmed mean or like those two-key stepped mean, median, those kind of things. Other robust whether those methods will work is my primary interest at this moment. And Dr. Ong mentioned that like you need I was originally going to briefly mention this, but Dr. Ong, like to decide the cutoff, we need to know, we need to decide the cutoff to know the K precisely. But also we have this kind of population depending quantity over here. So this is in fact not very desirable. Like in practice, you will need to plug in some kind of like estimators to this sigma square, for example. But this now is not fully accurate bound in that case. So whether we can avoid the use of this population quantity, whether we can make this quantity entirely some sample sense. That's I think some literature called that adaptivity, like not relying on the population quantity. And that's can be also an interesting direction, but as I mentioned, I'm mainly focusing on this direction at this moment. And thank you for your attention and welcome to the yes.
Where can we find the paper?
It will be uploaded pretty soon.
You mentioned that original estimate.
Yes.
When need estimate because they are considering
Right.
so, when the need is not an efficient
Mhm.
scenario when it's not really efficient.
Mhm.
So does this method improve or what does it will it help?
So like whether mean is efficient or not, it's not really matters as long as it can concentrate weakly. We can make it. We can still make it strongly concentrate. But in terms of efficiency, like there's a lot of things to say about efficiency. Efficiency, for example, in covariance matrix problem, whether the bounds is optimal with respect to the dimension E, that's totally another story because what our estimator achieves is only improving the rate with respect to the N. So in that sense, our estimator may get more efficient than original estimator in terms of N, but we don't know whether that's truly efficient compared to the other estimators, and that's something you have to manually check whether whether it has a better dimension bounds. And note that our estimator will fully depend on the behavior of our original estimator. So if you use the more efficient original estimator, you will get the more robust pressure median of estimators. Whenever you have the in fact, whenever you have the efficient estimator, you can get more robust, but that doesn't mean that it's fully efficient because there's other terms, for example, dimension, dependency on dimension, those kind of things. We don't know whether that would be also the optimal. Yeah. But in terms of N, you can always improve the estimator.
Any more questions?
Yes?
So I think you had mentioned at the beginning that this could be applicable in certain classes of discrete spaces.
Yes? symmetric graphs and trees. Metric graphs and trees.
So just for my own sake, so here trees, it's not trees in sort of the graph literature where it's undirected graphs with certain connectivity structures.
Um,
Metric trees. It's
it's similar, but just slightly different. Let me go here. So I think in like computer science, a lot of people regard tree as some kind of this kind of structure. But like it's almost similar but slightly different because like you can see here you have three neighbors, but these parent zones will only have two neighbors. So like in mathematically, like what people consider is something like this. So that it's kind of symmetric over all spaces. This is called a tree structure that goes in this literature. And if you just assign this matrix over these nodes, that makes a matrix. So like if you have just distance like 3, 2, 5, 7, these kind of things, that will make the matrix.
I see. So it's not metrics between different trees and the space of trees.
Oh yeah, that's also. Oh yeah, oh yeah. So some trees you can make it. For example, a space of phylogenetic trees. Like in that case, you need to specify which metric you want to impose, and certain metrics we can make certain trees and certain metrics. You can make space of trees to have a kappa structure as well, but not all the trees.
Any more questions? Okay, let's think them again. And we have some leftovers. We would like to have.